In the last module, we looked at the integrated momentum equation and one solution for a third order polynomial. We also started with the integral energy equation, but we couldn't go beyond a couple of steps. So, what we will do in this and the next module is look at the integral energy equation and try to obtain the Nusselt number using a third order polynomial for the temperature, non-dimensional temperature theta, and this would be done for a specific case of Prandtl number approximately equal to 1. I will also show you just the result for what happens to the formulation when you have an unheated starting length, that is where the thermal boundary layer starts to develop a little later than the hydrodynamic boundary layer. So, for getting started, we look at the energy equation. The energy equation, if you write, is written in this form: d by dx of u of t plus d by dy of v of t is equal to alpha d square t by dy square. This is after the boundary layer approximation, nu by Cp du by dy square. Okay. It actually is u dt by dx plus v dt by dy. When you start off with this form, this can be written as u dt by dx plus v dt by dy plus t times du by dx plus dv by dy. The du by dx plus dv by dy goes to 0 by continuity equation. So, the left hand side of the energy equation, rho Cp times u dt by dx plus v dt by dy can be written as rho Cp times d by dx of ut plus d by dy of vt. The rho Cp is brought down here and you get alpha, and mu over rho Cp is nu over rho Cp. This is the advection term, this is the conduction term, this is the effect of viscous dissipation, which is important only in high speed flows. So, let us now try to get the integral energy equation. We need to define a non-dimensional theta, which is T minus T infinity divided by T wall minus T infinity. This is a form that we are going to take. We can have any other non-dimensional form, but we will take this for now. We are going to say that for a general case, T wall is a function of x. Okay. T wall is a function of x. That means, if I have a flat plate, I have this as your thermal boundary layer is a function of x. T wall is a function of x. It is not a constant, it is a function of x. So, we are going to formulate the problem, formulate the integral momentum equation for the general case where T wall is a function of x. Viscous dissipation is also present in the formulation. So, we are going to retain this term and we will try to derive the most general form. Later on, for simplification, for getting a solution, we will eliminate couple of terms based on simplifying assumptions. Okay. So, if this is the case, we can write this as T is equal to theta times T wall minus T infinity plus T infinity. Therefore, d by dx of ut is equal to d by dx of, I am going to do one of the terms in detail, the other terms will be left as an exercise. I am going to substitute for t as this expression. This can be written as d by dx of u times t infinity plus d by dx of u theta T wall minus T infinity. I have just opened the brackets here. Now, I will differentiate this. This is T infinity du by dx plus u d of T infinity with respect to x plus, I am going to take u theta as one term and Tw minus T infinity as the second term. So, this is T wall minus T infinity d by dx of u theta plus u theta d by dx of T wall minus T infinity. 4 terms are there. and T infinity has been assumed to be constant. So, I did not write it here. So, T infinity is constant. So, this derivative goes to 0, T infinity is constant. This quantity T w is only a function of x, therefore, this partial derivative becomes a regular derivative. Regular derivative is always good compared to a partial derivative. So, this term becomes T infinity du by dx plus T w minus T infinity du theta divided by dx plus u theta d by dx of T wall minus T infinity. This is d by dx of ut. This is the first term on the left hand side. Okay. Now, the second term, which is the d by dy of Vt, I do exactly the same thing. Substitute for T, multiply by V. I can write this as T infinity dV by dy plus V dt infinity by dy plus Tw minus T infinity, exactly the same way, d by dy of V theta plus V theta d by dy of Tw minus T infinity. Notice this is also 0 because T infinity is constant. This one Tw is a function of x only, therefore, derivative with respect to y is 0. So, this term will drop off because Tw is only a function of x. So, I am left with the second term of the left hand side, d by dy of Vt is nothing but T infinity dV by dy plus Tw minus T infinity d by dy of V theta. This is something which we will keep aside. So, the left hand side we have written, the right hand side now we take first term alpha d square t by dy square, that is alpha d by dy of t, which is nothing but theta into Tw minus T infinity plus T infinity. D square T is d by dy times the derivative, and I have opened this way. So, I get this as T infinity is not a function of y. So, the derivative of this will go to 0. I have two terms here. So, d by dy of theta times T wall minus T infinity. T wall minus T infinity is a constant with respect to y, is only a function of x. So, it can come out of the differential sign. So, because it is only a function of x, it will come out of the differential sign, and therefore, I would get alpha T wall minus T infinity d squared theta by dy squared. This is my right hand side first term. Second term on the right hand side is nothing but nu by Cp d squared u by du by dy whole squared. This is just retained as it is. This represents one of the strong couplings between the momentum and the energy equation, retained as it is. So, we do not do anything to it. Now, the now the energy equation therefore becomes this term left hand side, this term left hand side we are going to write together, and I will use the next slide for this. So, energy equation becomes Tw minus T infinity d by dx of u theta plus d by dy of V theta this is the two terms that we have, see here. So, we have taken this term here and the corresponding term here. Okay. I am left with three other terms, this one and this one. So, T infinity, between this T infinity will come out common between these two, du by dx plus dv by dy. So, T infinity du by dx plus dv by dy, this is continuity equation, plus u theta d by dx of t wall minus t infinity as it is. This term is equal to 0 because this is continuity equation. Right hand side is nothing but alpha into t wall minus t infinity d squared theta by dy squared and nu over Cp du by dy the whole square as it is, right hand side. Now, I divide through by Tw minus T infinity. I will write energy equation therefore becomes d by dx of u theta plus d by dy of v theta. What was there? D by dx of ut, d by dy of vt, exactly the same form. We have an additional term which represents the effect of the wall temperature being a function of x. Right hand side, this one I have T wall minus T infinity here. Right hand side, T wall minus T infinity will cancel. So, I will get alpha d squared theta by dy squared plus nu over Cp T wall minus T infinity du by dy whole square. See this? This term and this term are exactly the same functional form as your original energy equation. D by dx of ut plus d by dy of vt is equal to alpha d square t by dy square and the additional term. This term has come in because of the variation in the wall temperature as a function of x, and this term has come in because of the viscous dissipation term modified by this algebraic operation. What do we do? Next step in the derivation is to integrate energy equation from y equal to 0 to some y equal to h. Remember, I could have a situation where this is my delta and this is my delta t, or vice versa, depending on the Prandtl number. Prandtl number greater than 1, we are going to have delta greater than delta t. Prandtl number less than 1, Prandtl number greater than 1, delta greater than delta t. Prandtl number less than 1, delta less than delta t. Prandtl number order of 1, delta is the same order as delta t. Whatever be the general condition of the fluid, the integration is carried over from y equal to 0 to some h which is far away from this delta or delta t. So, h is much greater than delta and delta t, whatever be the case. So, we do not have to worry about whether we are integrating this for which Prandtl number fluid, low Prandtl number, high Prandtl number, does not matter. Whatever be the variation, this so called h is far away from the wall, and therefore, the integration is possible. So, first term integrated is integral 0 to h d by dx of u theta dy. This is now going to be modified as d by dx, regular derivative. I am going to explain this. Let me write this down. Integral 0 to h u by u infinity theta dy. I have multiplied and divided by u infinity. Okay, this I have done. Taken the differential out and made it a regular derivative. Why? See, after I integrate this, when I integrate something here, first rule I am saying is that integration and differentiation I can change the order, that is the first thing. Second thing, when I want to do this is when I integrate something with respect to y, and supply the limits 0 and h or y1 and y2, so the y dependency is completely lost. That means this integrand, after evaluating the integral, only a function of x, right? You can do it with any arbitrary function. After you carry out the integration and put the limits, you will get the integrand to be only a function of x, and therefore what happens is that your differentiation after that, which is a partial derivative, will now become a regular derivative. This is something which is very, very important, makes our life easy. Second term here is integral 0 to h d by dy of v theta dy. This becomes v theta evaluated at h minus v theta evaluated at 0. What is v theta? Theta, if you go back to the definition, this is my theta. My theta is defined by this function. Sorry. This at 0, y equal to 0, t is equal to t wall, theta equal to 1. Theta beyond y equal to delta t, or y equal to delta means theta at 1 is equal to 0, because this is going to be t infinity for region at or beyond delta t. So, h is far away from the wall. So, theta at h is 0, theta at h is equal to 0. Therefore, this term will cancel off and we are left with minus v theta evaluated at 0. Theta evaluated 0 is 1. So, we are left with minus v at the wall, which is nothing but the suction or blowing velocity, which is Vw. So, two terms are now taken care of for integration. First term is changes to a ordinary differential with an integral inside. Second term reduces to minus Vw. Okay. Now, third term, which is nothing but integral u theta divided by t wall minus t infinity as it is, d by dx of t wall minus t infinity dy evaluated from 0 to capital H. This is what we need to do, and let us take a quick look at what is happening here. T wall minus t infinity is only a function of x. D by dx of this quantity is also only a function of x. So, these things can directly come out of the integral, this one. So, this can come out of the integral as 1 by t wall minus t infinity d by dx of t wall minus t infinity. Is that right? At best, this is a function of x. So, it can come out, and then I do exactly the same thing. U theta I multiply and divide by u infinity. So, u infinity u by u infinity theta dy 0 to capital H. I hope you understood. Multiplied and divided by u infinity, theta as it is, this whole thing is now coming out because it is only a function of y. This can be rewritten as 1 by t wall minus t infinity d by dx of t wall minus t infinity within brackets u infinity 0 to h u by u infinity theta dy, bracket complete. Fourth term, that is the thermal diffusivity, alpha d squared theta by dy squared dy is nothing but alpha d theta by dy evaluated at h minus alpha d theta by dy evaluated at the wall. What is this? This needs a little bit of explanation. What is the gradient at h which is far away? What is the gradient at h which is far away? 0. So, this term drops off because theta is equal to 0 at y equal to h or t equal to t infinity. You can write both. We are left with minus alpha d theta by dy evaluated at the wall, minus alpha d theta by dy evaluated at the wall. What is this quantity? This quantity, let us consider alpha d theta by dy evaluated at the wall. So, what is theta? T minus T infinity by T wall minus T infinity. So, d theta by dy is nothing but 1 by T wall minus T infinity dt by dy. Is that right? Correct. What is alpha? Alpha is k over rho Cp. So, this quantity is nothing but k over rho Cp 1 over T wall minus T infinity dt by dy evaluated at the wall. Is that right? Now, let us group this term. What is definition of heat transfer coefficient? H minus k dt by dy at the wall divided by some reference temperature difference. This is my definition of local heat transfer coefficient. Hx, this should be local temperature, Twx. It does not matter whatever the suffix is, subscript is. So, this quantity k dt by dy divided by T wall minus T infinity. You can see this here. So, this and this. What is this? Minus h of x, minus hx. So, minus local heat transfer coefficient divided by rho Cp, divided by rho Cp. So, therefore, this quantity minus alpha d theta by dy at the wall becomes, so this quantity, I am just putting this in black here, based on this simplification, you can write this as plus Hx by rho Cp. Minus is here, there is a minus, so this is Hx by rho Cp. Then last term, we are going to retain that term as it is. So, last term is integral 0 to h nu over Cp T wall minus T infinity du by dy whole squared dy. This is retained as it is. What happens to this? You can bring out this, can come out of the integral. Because it is a function of x only. That is the only manipulation possible. Okay. Now, I put all the terms together. Integrated energy equation is what I want to write. Recall, I am not sure whether I mentioned in the last module, we have to define an enthalpy thickness delta 2, which is called as the enthalpy thickness. This is analogous to displacement thickness or momentum thickness, which is because which is representing the effect of the presence of a boundary layer. The way of looking at it is momentum deficit caused because of a velocity profile. This difference in the velocity, this if this was u infinity and this green line represents the velocity profile, this black shaded part is the momentum deficit that is compensated by a momentum thickness delta 2. Same way, enthalpy thickness refers to the, because the temperature difference which is responsible for the heat transfer T wall minus T infinity is reducing. If there were no boundary layer, you would have T wall minus T infinity as the driving temperature difference. But because temperature changes progressively as I move up from the plate, the driving temperature difference reduces. And to account for this reduction, we define an enthalpy thickness analogous to momentum thickness. m dot Cp delta T is the energy carrying ability. So, based on that definition, enthalpy thickness is nothing but integral 0 to infinity. There is rho Cp u T minus T infinity divided by rho Cp u infinity T wall minus T infinity dy. This one would be the maximum possible, and this enthalpy thickness is what is the result of the formation of a boundary layer, and this can be rho Cp can cancel, this will be written as 0 to infinity u by u infinity T minus T infinity divided by T wall minus T infinity dy. This is my enthalpy thickness. This definition is very important, and in our nomenclature this T wall minus T infinity is nothing but, we call this theta, u by u infinity theta. Therefore, for our derivation, delta 2 is equal to integral 0 to infinity u by u infinity theta dy, u by u infinity theta dy. We will use this because this form appears everywhere. Where does this form appear? If you look here, I am showing you the third right hand side, left hand side term, u by u infinity theta dy. This will get directly replaced by the enthalpy thickness. So, using this definition and substituting this everywhere, I get integrated energy equation is d by dx of, what was my first term? My first term was this one. So, d by dx of u infinity as it is, this integrand is delta 2, second term is minus Vw as it is, third term this one, which is u infinity by Tw minus T infinity d by dx of Tw minus T infinity times delta 2. This integral is nothing but delta 2. Right hand side is h local divided by rho Cp as it is, this term, and the viscous dissipation term is retained as it was. Nu Cp by delta T can come out, nu by Cp T wall minus T infinity has come out, and you are left with integral 0 to h du by dy whole squared dy. Okay. So, this is my integrated energy equation, still not user friendly. So, I will open this bracket, this one I am going to just open it as delta 2 du infinity by dx plus u infinity d delta 2 by dx. What about this one? Delta 2 du infinity by dx, this one, minus Vw as it is, plus u infinity delta 2 by T wall minus T infinity d by dx of T wall minus T infinity is equal to hx by rho Cp plus nu by Cp blah blah blah. This is as it is, I am not writing. Okay. Now, I shall divide throughout by u infinity. I have u infinity here everywhere. So, if I divide through and just do the algebra 1 or 2 steps more. So, divide through by u infinity, I get d delta 2 by dx plus delta 2 as it is 1 by u infinity du infinity by dx plus 1 over T wall minus T infinity d by dx of T wall minus T infinity. This is my left hand side. Vw, I take it to the right hand side from here. So, Vw by u infinity would be there. This is equal to Vw by u infinity plus Stanton, local Stanton number, we will define that, plus nu by Eckert okay. This is my energy equation. Stanton number is nothing but H local by rho Cp u infinity, which comes out nothing but Nusselt by Re PR. You can check this. Okay. Stanton number is a representative non-dimensional heat transfer coefficient. So, the formula for this is here. You substitute all this. You had Hx by rho Cp, the u infinity was dividing throughout. So, you get Hx by rho Cp u infinity, which is Stanton number. The right hand side term, second one, u infinity, this is T wall minus T infinity, this one, and u infinity, this term. Eckert number basically is the ratio of sensible by kinetic energy, the Cp delta T, Cp delta T coming in the denominator. So, u infinity squared by 2 divided by Cp T wall minus T infinity. This is the definition of the Eckert number. You substitute for this. So, that is why you get 2 times Eckert number, 2 times the u infinity you have divided here. There is a u infinity, this is going to be 1 over Eckert number. So, u infinity cube comes from here, the 2 factor of 2 comes here because this 2 is sitting here, and this quantity nu remains as it is. So, u infinity squared by 2 Cp T wall minus T infinity. So, u this one is nothing but your Eckert number local. So, therefore, this is what is here, this is what is here. So, this is your integrated energy equation. Each term is non-dimensional, you can check that. It is an ordinary differential equation. What is it? It is an ordinary differential equation in x as the independent variable and delta 2 as the dependent variable, enthalpy thickness. So, your integrated momentum equation, if we go back, it was each term was non-dimensional, that was an ODE in momentum thickness. So, as engineers, the enthalpy thickness is related to the Stanton number, the momentum thickness is directly related to the coefficient of friction. In the next module, we will take up a simple case for solving this integral energy equation. We have solved the integral momentum equation. We will use the velocity, third order velocity profile from that, solve for the Nusselt number using a third order temperature profile for the case where Prandtl number is approximately equal to 1. Thank you.